Time is one of the most fundamental aspects of our existence, yet it remains one of the greatest mysteries of science and philosophy. We experience time as an unstoppable force, carrying us from the past through the present and into the unknown future. Clocks tick, days pass, and history unfolds, all reinforcing the idea that time moves in one direction. But is time as real as it seems, or is it merely an illusion shaped by our perception? Throughout history, thinkers from different fields have attempted to define and understand time. Classical physicists like Isaac Newton treated time as an absolute and independent entity, ticking away uniformly in the background of the universe. Then came Albert Einstein, who shattered this view by showing that time is relative. It stretches and contracts depending on speed and gravity. Meanwhile, modern quantum physics complicates the picture even further, suggesting that time might not even exist at the fundamental level of reality. Beyond physics, philosophers question whether time truly flows, or if past, present and future all exist simultaneously in a vast, unchanging block of reality. Some even argue that our brains construct time as a way to make sense of a universe that doesn't have a built-in flow of moments. So, is time a fundamental part of reality, or is it just a convenient way for our minds to organize experiences? As we explore the physics of past, present and future, we'll uncover the surprising and mind-bending truths about time itself. Time feels intuitive. We measure it in seconds, minutes and years, watching the hands of a clock move forward. But what exactly is time? Is it a real, physical entity, or just a way for humans to track change? In our daily lives, time is a tool for organizing events. We say the sun rises in the morning and sets in the evening, and we use calendars to mark days, months and years. However, science suggests that time might be much more or less than we assume. Some physicists argue that time is just a way to measure motion and change. Without movement, time might not exist at all. Others believe that time is a fundamental part of the universe, woven into the very fabric of reality. From a practical perspective, time is what allows us to schedule meetings, cook meals, and recall memories. It gives order to our experiences, separating what happened before from what will happen next. However, in the realm of physics, time is far less straightforward. Classical physics treats time as an independent, continuous flow, while Einstein's theory of relativity suggests that time is flexible and linked to space itself. Meanwhile, quantum mechanics presents an even stranger possibility that time may not exist in the way we think. Before we dive into the physics, we must ask, is time something that truly exists, or is it just a concept we've invented to make sense of the world? For centuries, time was thought to be an absolute universal quantity. Isaac Newton, one of the greatest physicists of all time, believed that time flowed at a constant rate, independent of anything happening in the universe. In his 1687 work, Newton described time as an invisible, unchanging background against which all motion occurs. According to this view, a second on Earth is the same as a second anywhere else in the universe. Time marches on uniformly, unaffected by speed, gravity or motion. This idea of absolute time fit well with everyday experiences. Clocks seemed to tick at a constant pace, and past, present and future appeared to be well defined. However, while Newton's laws were incredibly successful at explaining planetary motion and mechanics, his understanding of time would later be challenged. Newton's physics painted a picture of a clockwork universe, a reality where events unfold predictably like the gears of a giant machine. Time was merely a parameter used to describe motion, and the future was entirely determined by the present. If we had complete knowledge of every particle's position and velocity, we could, in principle, predict everything that would ever happen. This deterministic view of time dominated scientific thought for centuries, but cracks in the foundation began to appear in the early 20th century. With the rise of Einstein's relativity, the concept of absolute time was shattered, leading to a radical rethinking of time itself. Newton's idea of absolute time ruled physics for centuries, but in the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He showed that time is not universal, it is relative, meaning it changes depending on speed and gravity. This discovery shattered the classical view of a clockwork universe where time ticked forward the same way for everyone. At the heart of Einstein's theory is a simple but profound idea. Time and space are interconnected. Instead of existing separately, they form a four-dimensional structure called space-time. In this new model, time is no longer an independent backdrop but a flexible dimension that can be stretched, compressed, and even slowed down. One of the most famous consequences of Einstein's theory is time dilation, the idea that time passes at different rates for different observers. This effect becomes noticeable at extremely high speeds, close to the speed of light. Imagine two identical twins. One stays on Earth, while the other travels into space on a high-speed rocket. When the space-traveling twin returns, they will be younger than the twin who stayed on Earth. This is not science fiction, but a real measurable effect confirmed by experiments with atomic clocks placed on fast-moving planes and satellites. Time slows down for objects moving at high speeds relative to a stationary observer. The faster you go, the slower your clock ticks compared to someone at rest. If you could somehow travel at the speed of light, time for you would completely stop. Einstein's relativity also changed our understanding of gravity. Instead of being a simple force pulling objects together, gravity is actually the curvature of space-time caused by massive objects. Picture a trampoline. If you place a heavy ball in the center, it bends the surface around it. A smaller ball rolling nearby will follow the curve of the trampoline, appearing to be attracted to the larger one. In the same way, massive objects like planets, stars, and black holes bend space-time, affecting how time flows. The stronger the gravitational pull, the more space-time is curved, and the slower time moves. This effect, known as gravitational time dilation, means that time runs slightly faster on a mountaintop than at sea level because gravity is weaker at higher altitudes. On the extreme end, near a black hole, time slows down so much that an observer far away would see events happening in slow motion. Einstein's theory completely overturned our intuitive sense of time. If time flows differently depending on speed and gravity, then there is no single now that everyone in the universe experiences simultaneously. The past, present, and future are not absolute but depend on where and how you are moving. This raises deep philosophical questions. If time is relative, does that mean the past and future exist just as much as the present? Could our perception of time flowing forward be an illusion? Is time something fundamental or just a feature of how we experience the universe? Einstein's discoveries reshaped physics, but they were just the beginning of an even stranger journey into the nature of time. As we dive deeper, we'll see how quantum mechanics, thermodynamics, and modern cosmology challenge everything we think we know about time itself. We experience time as something that moves forward, from past to present to future. We remember yesterday, live today, and anticipate tomorrow. A dropped glass shatters but never spontaneously reassembles. Smoke rises from a fire but never returns to the wood. This one-way direction of time is known as the arrow of time, but why does time move forward and not backward? Interestingly, the fundamental laws of physics, including Einstein's relativity and even quantum mechanics, are time-symmetric. They work the same way whether time moves forward or in reverse. If we were to watch a recording of two particles colliding and then play it backward, we wouldn't be able to tell which was the real direction. Yet in our everyday world, we only experience time moving forward. So what creates this irreversible flow? The best explanation for the arrow of time comes from thermodynamics, specifically the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in an isolated system. Imagine a deck of cards that starts in perfect order. If you shuffle it, the arrangement becomes more random. The more you shuffle, the less likely it is to return to the original order. The same principle applies to everything in the universe. Systems naturally evolve from order to disorder. This increase in entropy gives time its apparent direction. A broken glass is more disordered than an intact one, and natural processes always tend to move toward greater disorder. This explains why we remember the past but not the future, because the past was a state of lower entropy, while the future holds increasing randomness. Entropy alone doesn't explain why time started moving forward in the first place. To answer that, we must look at the Big Bang. At the beginning of the universe, everything was in an extremely low entropy, highly ordered state. As the universe expanded, entropy increased, setting time's arrow in motion. This raises a profound question. What if the universe eventually stops expanding and begins to contract? Could time then reverse? Some physicists speculate that if the universe collapses in a big crunch, entropy might decrease, potentially causing time to flow backward. However, this remains a theoretical idea with no experimental evidence. Even though time reversal is mathematically possible in physics equations, it doesn't happen in reality because of entropy. Once disorder increases, it's nearly impossible to reverse naturally. That's why we see eggs break but never unbreak, and why we age instead of growing younger. In essence, the arrow of time emerges not from the fundamental laws of physics, but from the way our universe began, highly ordered and expanding, with entropy constantly increasing. But could there be deeper layers to time's nature? In the next section, we'll explore quantum mechanics, where time behaves in even stranger ways. At large scales, time appears to flow smoothly, and the laws of thermodynamics dictate its direction. However, when we zoom into the level of atoms and subatomic particles, the nature of time becomes far stranger. Quantum mechanics, the branch of physics that governs the microscopic world, challenges our classical understanding of time in several fundamental ways. In classical physics, time is treated as a continuous and universal parameter, something that simply ticks forward. But in quantum mechanics, time plays a very different role. The Schrödinger equation, which describes the behavior of quantum systems, is time-symmetric. It works just as well whether time runs forward or backward. Unlike in thermodynamics, there is no built-in arrow of time at the quantum level. This means that, in theory, quantum processes should be able to evolve in both directions, making time's flow seem less fundamental. This raises an important question. If time doesn't naturally flow forward in quantum mechanics, where does our sense of past, present, and future come from? Some physicists believe that time's direction only emerges when quantum systems interact with larger, more complex systems, such as an observer making a measurement. One of the biggest mysteries in quantum mechanics is the measurement problem. Before a measurement is made, a quantum particle exists in a state of superposition. It can be in multiple states at once. However, when we observe it, the superposition collapses into a single definite state. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that this collapse is what chooses a single outcome and gives us a definite reality. But this raises a strange possibility. Could the act of measurement itself be what forces time to appear one-directional? Other interpretations, such as the many worlds interpretation, propose that all possible outcomes of a quantum event occur in parallel universes. If this is true, then time may not be a single flow, but rather a branching structure where all possible futures coexist. Another quantum phenomenon that challenges our understanding of time is quantum entanglement. When two particles become entangled, their states remain linked, no matter how far apart they are. If we measure one particle, the other instantly knows and adjusts its state accordingly. Even more bizarrely, Some experiments suggest that actions taken in the present can affect measurements of a particle's state in the past. This concept, known as retrocausality, implies that the future might influence the past, which directly contradicts our everyday experience of time. Some physicists believe that time might not be fundamental at all. It could be an emergent property that arises from quantum interactions. Just as temperature is not a fundamental property of a single particle, but emerges from the collective behavior of many particles, time might emerge from the way quantum systems behave at a larger scale. This idea is supported by research in loop quantum gravity, a theory that attempts to unify quantum mechanics and relativity. Some versions of this theory suggest that time may not exist in a fundamental way, and that what we experience as time is just an illusion caused by how we perceive change. Quantum mechanics challenges the very foundation of how we perceive time. At the smallest scales, time appears reversible, measurements create uncertainty, and entanglement suggests connections that defy classical cause and effect. If time is not fundamental, then our entire perception of reality may need to be rethought. But what if time itself is already set? If past, present, and future all exist simultaneously? In the next section, we'll explore the block universe theory and what it means for the nature of time. If time is truly relative, and if quantum mechanics challenges its very nature, could it be that time doesn't actually flow at all? One of the most mind-bending ideas in physics is the block universe theory, which suggests that past, present, and future all exist simultaneously, just like different locations on a map. The block universe theory, also known as eternalism, comes from Einstein's theory of relativity. According to relativity, time is just another dimension, like the three dimensions of space. Instead of events happening in a flowing timeline, all moments in time, past, present, and future, are equally real and exist together in a vast, four-dimensional structure called space-time. In this view, we don't move through time like a river. Instead, we are simply experiencing one particular slice of a timeless reality. Every moment, your birth, this very second, and the distant future already exists somewhere in this block. The feeling of now is just an illusion created by our conscious experience. There are several reasons why physicists take the block universe seriously. In relativity, simultaneity is relative. Different observers moving at different speeds will disagree on what events happen at the same time. This suggests that there is no single universal now, supporting the idea that all moments exist at once. Time slows down for objects moving at high speeds. If time were absolute, this wouldn't be possible. The fact that time is flexible suggests that it might be more like space, where all locations exist simultaneously. Many of the equations that describe the universe treat time as just another coordinate in a larger structure. If time were truly flowing, we might expect to see something in the math that accounts for this motion, but we don't. If the block universe is real, it raises deep philosophical questions. If the future already exists, does that mean our choices are predetermined? Is free will an illusion since all our actions are already part of the block? Can we change the future, or is it as fixed as the past? Many scientists argue that while the future might already exist in the block, our experience of making choices is still meaningful. Even if our path is set, we don't have access to the future, so we still experience time as if it's unfolding. If time is just another dimension, could we theoretically move through it like we do in space? Some theories suggest that time travel might be possible if we can manipulate space-time, such as through wormholes or closed time-like curves. But so far there is no experimental evidence for this. So is time real, or is it just a construct of our minds? The answer depends on how we define real. If we view time as a fundamental property of the universe, relativity and quantum mechanics suggest that it behaves very differently from how we experience it. If we adopt the block universe view, time is just another dimension, and our experience of now is an illusion. If time is emergent, then it might not be a fundamental part of the universe at all, just a way for us to describe change. Whatever the true nature of time is, one thing is certain: our understanding of it is far from complete. Future discoveries in physics may one day reveal whether time is a fundamental part of reality or just a product of our perception. Until then, we remain trapped in its mysterious flow, or perhaps just a frozen moment in the vast, unchanging block of existence.